Hello, in today's video we're going to be discussing section 7.2, graphing exponential functions. So to graph exponential functions, first we're going to explore a couple different scenarios. So I'd like for you to take a moment and consider the function f of x, which is equal to 2 times 2 to the power of x, and plug in our x values to find the y values and sketch yourself a brief graph of our exponential function. When I plug in a -3, I get 2 times 2 to the -3rd, or 2 times 1/8, which reduces to 1/4. 2 times 2 to the -2nd power is going to simplify to 1/2. 2 times 2 to the -1st is going to simplify to 1. 2 times 2 to the 0 is 2. 2 times 2 to the 1st is 4. 2 to the 2nd times 2 is 8. And 2 to the 3rd times 2 is 16. And I will plot these on my graph. So I have -3 1/4, which is approximately here. I have -2 and 1/2, which is about just a little bit higher. -1 and 1, 0 and 2, 1 and 4, 2 and 8, 3 and 16, which is off my graph. Now when I go to connect these dots to sketch my graph, I want to think about what happens beyond these points. So as I move to the right on my x-axis, my x values get larger and larger and larger. So as this x increases, then my f will increase exponentially. We're just multiplying by 2 for every unit that my x increases. So there is no boundary on that right side of my graph. So my graph is going to go up to the right forever. So I will put an arrow on that end. Now on the left-hand side, my x's are approaching -infinity. So as these x's become more and more negative, what happens is we are dividing by a larger and larger number. So for example, if I try putting in an x value of maybe -10, what I end up with is 2 times 2 to the -10th power, which is really 2 times 1 over 2 to the 10th. So this is a very, very small number. If I make this 100, I have a -100, and 2 to the 100 is in the denominator. If I make this 10,000, 10,000, 2 to the 10,000 is still in the denominator. It doesn't matter how negative we make our x value, our y value is never going to get negative. The reason is that negative x value just creates a fraction. Since it's in an exponent, it creates a fraction, but my y value still stays positive no matter how negative my x value is. So no matter what, in this case, my y value will never be negative, and it will never hit 0. As we move more and more negative, my graph will continually become smaller and smaller and smaller, but it will never hit 0 or cross over into the negatives. So my end behavior, as x approaches positive infinity, my graph f of x is going to increase or go up. So as we move to the right, my graph goes up infinitely without bound. And as x approaches -infinity, so now we're moving to the left, my y value decreases, but there's a boundary. It's never going to hit or cross 0. So my f of x function does get smaller, but it does not cross 0, so it only approaches 0. Go ahead and take a moment to try this next one on your own. We do have a fraction as our growth factor, but we're going to go through the process very similarly to the one that we just completed. So go ahead and take a moment, pause the video, and try this one on your own. When I plug in a -3, I've got 3 times 1/2 to the -3rd, which is actually 3 times 2. This is a 1/2. Let me clean that up a little bit. So 3 times 1/2 to the -3rd, which is actually 3 times 2 to the 3rd, which is going to be 24. 3 times 1/2 to the -2nd is going to be 12, times -1, or to the power of -1 is 6, to the power of 0 is 3, to the power of 1 is 3 over 2. Then I have 3 over 4 and 3 over 8. So graphing these, I've got negative 324, which is off my graph, negative 212, which would be right around here, negative 1 and 6, 0, 3, 1 and 3/2 or 1.5, 2 and 3/4, 3 and 3/8, which is a little bit less than 1/2. And my graph is going to look something like this, more or less. Let me try that again. I think I can do better. Not much, but a little bit. Okay, so on that right-hand side, as my x's become more and more negative, as this x value becomes more and more negative, what happens is that my x value, if it is negative, is going to flip my 1/2 over into a 2. So I will have 3 times 1/2 to some negative number. It doesn't matter what that negative number is. If that number is negative, that fraction then becomes a 2 or 2 over 1. So if I have negative 10, what I actually have is 2 to the positive 10th power, which is a fairly large number. As my x increases to 100, I then have 2 to the 100th power, which is very, very large. That x value can be as negative as we want. There aren't going to be any problems. So in this case, as x approaches negative infinity, my f of x, or in this case g of x graph, is going to approach positive infinity. On the other hand, as x approaches positive infinity, so now we're moving to the right on my graph, as these x values become larger and larger and larger, I've got 3 times 1/2 maybe to the 10th power. So we're multiplying by 1/2 10 times. That makes our 3 very, very, very small. If we do it 100 times, 3 is significantly smaller. 1,000 times, 10,000 times, we are multiplying by 1/2 10,000 times. That makes that 3 very, very, very small. However, while it is extremely close to 0, it will never actually equal 0, nor will it be negative. So similarly as our last graph, g of x will only approach 0, but it will never cross over or equal 0. Here are some special features of our exponential graphs. They are one-to-one functions, which means that they are invertible. They have a vertical intercept at 0a. So if I go back and look at my g of x function, there's going to be a vertical intercept of 3. And the reason that is that when I put in a 0 for x, this base to the power of 0 is just 1, which leaves me with that multiplier of 3 as my vertical intercept. Similarly here, my vertical intercept is 2, which came from that multiplier on the front of my exponential component. So my vertical intercept is going to be that coefficient on your exponential component. So long as you have no translation, so we're not shifting our graph vertically in any way, your horizontal asymptote is going to be y equals 0. This can change, just like when we were graphing sine and cosine functions. That midline moved up and down depending on whatever vertical shifts we had on our graph. But if there are none, our home base is for your horizontal asymptote to be at 0. Our domain, we can use any x value we want, so we go from negative infinity to infinity. My range, as long as there are no vertical shifts, we cannot ever cross over or equal 0. So we are going to have a range that is only greater than 0. Now this is assuming that we're only dealing with positive a values. Here we are told that a is greater than 0. We can work with negative a values, but that would reflect your graph vertically into the third and fourth quadrant where y is negative. Now if your b value is greater than 1, that means that when you multiply by a, you will be increasing your value of a. So your graph will start small and it will grow as your b value increases. But if your b value is between 0 and 1, for example 1/2 like we saw in the last graph, every x that we input is going to multiply by another factor of that 1/2, making our function become smaller and smaller as the x increases. So that would allow us to have this decreasing function. So let's take a look at these three graphs and match the graphs with their corresponding function. And we are going to look at what effect the parameter a is going to have on our graphs. So one thing that we talked about in our last slide is that the value of a is going to tell you your vertical intercept. So here, if I'm looking for the value of a, that would be the number that we are multiplying this base by, and that would be 1. So this graph is going to have a point at 0, 1. So my vertical intercept will be 0, 1. There's only one graph that has a point on 0, 1, and that would be this graph to the far right. So this function I'm going to label as f of x. Go ahead and take a moment to try out those next couple. My g of x function has a multiplier of 2, which means that I'm going to have a vertical intercept at 0, 2. So between those next two graphs, I only have one graph with an intercept of 2 for y, which means that that middle graph is going to be my g of x, which leaves my third graph to be h of x, but let's go ahead and check. So my a here is 5, so I have 0, 5. So my vertical intercept is 5, and sure enough, that gives me my third graph of h of x. So altering the parameter of a changes my vertical intercept, but if we look, it also causes our graph to increase at a greater rate. So what effect does altering the parameter of a have? It is going to affect the vertical intercept and the growth rate. So we've got a couple other graphs to look at here. Go ahead and take a moment to see what effect changing the value of b is going to have on the graphs of our exponential functions. So I've got f of x is equal to 2 to the power of x. So my vertical intercept here is 1. Well, all three of them cross at 1, so we're going to need to be a little bit more specific. I do know that this is a growth function, so we're looking at one of these two on the right-hand side, and the reason I know that is because my b value is greater than 1. Here my a is 1, and b is greater than 1, which means that it is a growth function. So to figure out which of those two it is, I'm going to try plugging in a value of 1 for x and seeing if I will get 2 or 3 for that y value. So f of 1 is equal to 2 to the power of 1, so f of 1 is equal to 2, which means that we are looking at this graph on the far right as my f of x function. Now I look at g of x. G of x is equal to 1/2 times to the power of x. Here my b value is greater than 0, but it is less than 1, which means this is a decay. There is only one decay graph here in our coordinate plane, which tells me that this must be g of x. Starts large and decays as our x values increase, which means that h of x must be our remaining graph, but I'm going to go ahead and check that out. H of x is 3 to the power of x. My a value is 1 and my b value is greater than 1, which does mean that this is a growth function. So it is possible for it to be that third remaining graph, but I'm going to go ahead and test by plugging in a value of 1. So h of 1 is 3 to the power of 1, so h of 1 is 3. When I have a value of 1 for x, I have a value of 3 for y, and sure enough, that puts me on that middle graph. So altering the parameter of b is again going to affect our growth rate, and it will determine if your graph is growth or decay. That brings us to the end of section 7.2. Thanks so much for watching and have a great rest of your day.